find the eigenvalues and eigenvectors for a given matrix. For eigenvalues, we will solve the characteristic equation. And that is the determinant of the matrix A minus lambda times identity matrix equal to 0. In this case, that is the matrix A. So that is the eigenvalues. For eigenvectors, we will solve this equation: A minus lambda I times vector V equal to a 0 vector. Notice that on the left hand side, this equation is in the scalar form, and this one is in the vector form. And the reason we have that because we're looking for the set of eigenvalues and eigenvectors in this form. So if we move everything on the left hand side, we have this. We cannot just factor out the V. If we do that, it doesn't make any sense. By the way, that is the 0 vector. If we do that, that doesn't make any sense. So we have to put the matrix here. So we have a matrix, subtract a matrix. So that makes sense. And this vector equation, this matrix equation, must have infinitely many solutions, or we should say non-trivial solution. So the determinant of this matrix has to be equal to 0 for it to have infinitely many solutions, or it has non-trivial solution. Alright, anyway, now we do the math. We find the determinant of the matrix A. The matrix A minus lambda times I. So all we do is just rewrite the matrix A and then subtract lambda on the diagonal. So pretty much we have like the matrix A. If we rewrite that, minus lambda times the identity matrix, where we multiply lambda in, and then we subtract. So pretty much we just subtract lambda on the diagonals from the matrix A, and then we find the determinant of a 2 by 2 matrix. So we do, we just multiply in this direction and then minus that direction. So we have 1 minus lambda times minus 6 minus lambda minus 30 equal to 0. Now we're going to solve for it. Multiply it out, negative 6 negative lambda plus 6 lambda plus lambda square minus 30 equal to 0. And then rewrite that 6 plus 5 lambda minus 36 equal to 0. Factor out, we have lambda plus 9 lambda minus 4 equal to 0. So lambda equal to negative 9 and lambda equal to 4. Those are the eigenvalues. The eigenvectors will correspond to lambda equal to negative 9 or lambda equal to 4. So first, for lambda equal to negative 9, we're going to solve that equation. So pretty much we have A, matrix A, 1, 30, 1, and negative 6. We subtract lambda on the diagonal. Minus negative 9 is a plus 9. We take that matrix times the vector v. We can just say v1, v2 if we want to, equal to a 0 vector. Right? So rewrite this matrix. We should have 10, 30, and 1, and 3. V1, V2. Right. This is a 2 by 2. It should be easy. We see that right away. But I'm going to use the calculator because later on we go to a 3 by 3 matrix. It will be easier if we have reduced the matrix. Right. So what I do is I put this into an augmented matrix and then do the reduced row echelon form. So first, second matrix, go to math and reduce row echelon form, and then we put the matrix alpha zoom. It has 2 rows, 3 columns, and we'll have 10, 30. By the way, if your calculator cannot do this, don't worry, I'm going to use that different way later. By the way, when we enter in this form, do not hit enter, just hit this arrow instead. Next, and then next. Right. Of course, that should be simple. So when we do the reduced row echelon form, we end up with 1, 3, 0, 0, V1, V2, 0, 0. The bottom row doesn't give us anything. So we need to do just multiply the first row with the V1, V2. So we have V1 plus 3V2 equal to 0. And of course we can choose V2 to be something and choose V1 to be something. But from this one, if we choose V2 to be arbitrary, then we have V1 equal to negative 3V2. This is a little bit longer than it should be, but I think it's easier when we write like this. So we have V1, V2, the solution. V1 is negative 3V2, and V2 is just V2. If we factor out V2, we have negative 3 and 1. And we can choose this to be the eigenvector. Again, eigenvectors is actually a space. So we just choose the convenient one to be the eigenvector. So this is an eigenvector corresponding to the eigenvalues of lambda equal to negative 9. I said this is a little longer than it should, but I think it is easier to understand. And now we do the same thing, but this time for the eigenvalues of 4. Right, so we do the same thing. We'll take the matrix 1, 30, 1, 6, and we subtract the eigenvalues on the diagonal. Multiply V1, V2 equal to a 0 vector. So we will have negative 3, 30, 1, negative. Oh, sorry. It's negative 6. That's negative 10. v1, v2, 0, 0. And we do the reduced row echelon form here. This time I'm going to use the matrix in the TI-83. So if we have TI-83, then we have to store the matrix. So hit second, that matrix button. I'm going to store into the matrix A. This one is 2 rows, 3 columns. In this mode, we're going to hit the enter key. Right, -3, 30, 0, 1, -10, and 0. Of course, we should put this in the Mantix matrix, but I skipped that step because we can easily see that just pretty much on the coefficient here. Right, so we have that matrix, and when we're done, just hit second and quick, and second matrix again. Go to the reduced row echelon form, but this time we apply that to the matrix A. So under names 1, hit enter. Of course, we don't even need the calculator for this form, but I just want to show you this. So later on, when we have the 3 by 3, we can do that as so it will be easier when we have the 3 by 3 with the calculator. Again, the last row of 0 doesn't help us. Only the first row of v1 minus 10 v2 equal to 0, which gives us v1 is 10 v2. Now if we write the solution as v1 and v2, where v1 is 10 v2 and v2 is v2, factor out v2, we have 10 and 1. And we choose 10 and 1 as the vector corresponding to eigenvalues of 4. So in fact we can, and we should write like this: lambda 2, that the eigenvalues of 2, we have eigenvector corresponding to that is 10 and 1. And for lambda 1, the eigenvalues, we have the eigenvector. This is the vector -3 and 1. So let me zoom out to have the whole problem. So the eigenvalues, we solve the characteristic equation. And then we have the eigenvectors. Eigenvalues and the eigenvector goes hand in hand. They a pair corresponding to an eigenvectors is an eigenvalues. So we find eigenvalues first using the characteristic equation, and then we find eigenvectors.